right, so let's look at a couple of examples of using this torque application. So let's say this is the Atwood pulley. Like we've seen before, but instead of having a massless, frictionless pulley, our pulley now is going to have some mass. So I'm going to draw that situation. So this mass, we're going to call M1, and it's going to be 2 kilograms. This is going to be mass 2, and it's going to be 3 kilograms. Now the pulley is massful, not massless. So the mass of that little pulley, we're going to make it 1 kilograms, and then the radius of the pulley will be 20 centimeters, so 0.2 meters. Okay. Now, there's little bit of friction in this axle, but not enough to cause a significant amount of torque or slowing down. Now, summing the forces on these guys right here will be the same as we always have. So can we find the acceleration and tensions? And yes, plural. Because in order to make that disc spin, so this pulley is a disc, and it has a mass, in order to get something to accelerate, like it's going to go from not moving to moving, so there is going to be an acceleration of our pulley. In order to get it to move, what do you have to have on the system in order to get it to move? There has to be not just a force, but like right now, are you accelerating as you sit there in your seat? No, because what? You're in equilibrium. So in order to get you to accelerate, what do we have to do? What about it? Not just force, an unbalanced force. There has to be unbalanced forces. Now there are forces acting on this disc, and they are in like tug of war. It has to be tangential to the circle in order to get it to rotate, yes. So, just like we have before, to find the acceleration, we can sum their forces, so we need our free body diagrams first. So let's draw the force diagram for the 2 kilogram mass that I called M1 to make things super confusing. It's going to have a weight just like any other hanging mass would have, and there's a tension in the cord. This is all like first semester review stuff. And that tension now is going to be different than the other tension, because if they're the same, the wheel will not accelerate. The wheel will not turn because the forces would be balanced and it would be in equilibrium. But if you're going to get the wheel to turn, it's got to go from not moving to moving, so there has to be a net force. So there has to be different tensions on the cords. The 3 kilogram mass, which I drew as a triangle, would have a different tension up on it, and it would have its weight. And then we have to draw the pulley. So 2/3 of the stuff that we've done here is old. Now, there is a tension force from mass 1, and there's a tension force from mass 2. If we were drawing all the forces acting on our pulley, we would also have a normal force from the pivot, and doesn't the pulley itself have a weight? it didn't work. All right, this is going to be the longest video of all time. Jess, I hope you watch this. All right, so these are all the forces acting on the system. Now, just like we've done before, it's a really good idea to define some direction. Like, which way do you think the 2-kilogram mass will move? Up or down? This is a 3-kilogram on the right side. There's a 2-kilogram on the left side. Okay, so do you want up to be the positive direction? And which way does the 3-kilogram mass move then? Down, so make that the positive direction. Now, which way do you think the disc of the pulley is going to rotate? Clockwise, counterclockwise, or not at all? Clockwise, because the big guy's over here. So let's make clockwise positive to make things nice. So let's sum the forces in the y direction on this M1. Now, because both of these objects are connected to the same rope, they have the same acceleration. They are both going to move the same distance in the same amount of time, so they have to have the same acceleration. We'll look at a case in a minute that doesn't have that same. So FT1 minus FG1 would equal M1A. Does that seem familiar? All right, so then let's do this one. Let's sum the forces in the y direction, and they would equal M2G, and we'd have FG2 minus FT2 is equal to M2A. So far, so good? So again, 2/3 of what we've done so far is stuff you've done before. So let's now look at the new thing. The new thing is this wheel business. So I'm going to scoot over just a little bit. Now, instead of, we can sum the forces. Let me just, summing the forces in the y direction should be 0, because what does our wheel move? Does it move up and down, left or right? No. It spins around a fixed point, but it's not translating. It's rotating. Translating means moving in a straight line. The center of mass is going to change positions. That doesn't happen. If I were to sum these forces, then I would have the normal force is up. We have a gravitational force that's down. We have a FT1 that's down, and we have an FT2 that's down, and that's 0. So we can come back in a minute and find the normal force acting on our disc, but I don't know FT1 and FT2. Now, I can sum the torque, and because it's rotating, it will be equal to I times alpha. Now, if you go back to our picture up here, FT2 is causing it to rotate clockwise, so that's going to be our positive torque. So FT2, and remember torque is F times R, but then the other force, FT1, is opposing this motion, so FT1 times R would be equal then to I alpha. Now, I've got this angular acceleration and I have linear acceleration. There's a really important connection between these two. Actually, I'm going to start over. So side note, arc length, S is equal to R theta, right? Yep. If I divide by time on both sides, then I get I get velocity is equal to R omega. If we divide or if we have a change in velocity, I should have put a change here. Bad teacher. Sorry, Jess. If we have a change in velocity over a change in time, and a change in angular speed over a change in time, change in velocity over change in time is what? Acceleration. Very good. It's acceleration. And so R And what would change in angular speed or angular velocity over change in time be? Angular acceleration. Very good. This right here is essential for your success. Let's bling it out here. Okay. Woo, woo. He's so important. So important. That is going to be the connector between this acceleration, and that angular acceleration. We have to connect them. Okay, so look, this is my plan. How about let's solve for ft1, solve for ft2. We'll stick it back in ft2, we'll stick ft1 back in here. We'll make a transformation between angular acceleration and linear acceleration, and then we should be able to solve for the acceleration of the system. And once we get the acceleration of the system, we can go back up here and find both the tensions. So that's the plan. Okay. Still can't pause. You just have to fast forward through the random talking. All right, so help me out. ft1 would be what when we rearrange?
M1A plus FT.
And ft2 would be fg2 minus m2a. Is that right?
It will be
Here we go. So then for our torque equation, we need F2, which would be Fg2 minus M2A, but all times are minus the Ft1, which is M1A plus F sub G1, all times R, is equal to I times alpha. So that's just substitution into our torque equation from right above. So then M2G R minus M2A R minus M1A R minus M1G R would equal, what's the moment of inertia for a disk? 1/2 M R squared? It's squared. And if acceleration is equal to R times alpha, then what's alpha? Yes, that would be A over R. So we can put an A over R. You're about to see something that looks magical. What can you do now? Oh my goodness, let's go get a big, fat, red lightsaber and cancel some stuff. What can I cancel? Ooh, can I cancel an R and an R? But will I still have an R and an R and an R and an R and an R? Boom! So when both of the strings are at the same radius, you're right. The radius winds up canceling out. So that's a lovely prettiness there. All right, so I have M2G. I need to get my acceleration together, so I'm going to have minus M1G is equal to 1/2 M3, that's the pulley, times A. But I'm going to add over both of these other acceleration terms, M2A and M1A. All right, so if I wanted to try to find the acceleration at this point, could we just factor out an A on the right side and divide by the stuff? So could we do M2G minus M1G all over 1/2 M3 plus M2 plus M1 is equal to A? How about that? Who's got a calculator? All right, here we go. So do you even remember the masses? I do. All right, so M2 was 3
Yeah.
minus M1 was 2. 1/2. The mass of the pulley was 1 plus 3 plus 2. So what is our acceleration? What is 10 divided by 6? 5.5? 5.5?
1.81.
I agree. How are we going to find the tension now?
You can plug it right in.
We got to plug it in, plug it in. All right. Yeah. So then FT1 would have been what? FG1 plus M1A. Was that correct from up there? So that's M1G plus M1A. So that would be 20 plus 2 times 1.81. And then FT2 would be FG2 minus M2A. So that would be like 30 minus 3 times 1.8. Well, the tension of the first one should be like 23.6. Beautiful. And then what about the tension on the other side?
30 minus 3. This is 24.6.
Are they the same? So these forces are unbalanced, thus there can be acceleration. Ah!
Acceleration for both of them.
The acceleration of the rope is the same. But because these two tensions are different, so you've got 23.6 over here and you've got 24.6 over here. So which way is it going to turn? Uh-huh. Now let's go back. What would the normal force on that pulley be? It would have to be equal to the weight of the pulley and each one of the tension forces. Didn't we write our free body diagram and write the equation for the forces there? So that would be.
I thought Fn equal Fa minus F2 or minus F2.
Why would it be?
That's the road down.
Yes, and then I added them all to the right side. So solve for the normal force there. So they would be all added up together. And so 10 plus 23.6 plus 24.6. What do we get? What's that? You can replace. All right. So what's cool about this problem though is that the force that the axle has to apply to the system to keep it from moving is that normal force, and it's way more than the weight of the object. And it's more than the sum of the weights. So think about it. What's the total weight of the system? It's 1 kilogram plus 2 plus 3, so 6 kilograms is the total mass of the system. So if you were looking at the total weight of the system, it would be 60 newtons. Why is it different? Why is it not 60? Because it's moving.